Hello, I'm Brian Wargo, and I've been teaching for about 30 years. Today's lesson is on calculus, one of the greatest ideas of all time. Unfortunately, it's also one that instills fear in both teachers and students. Over the years, I've developed some pretty good lessons, ones that work in the classroom. I'm going to share that today. I also co-founded the Idealized Science Institute. We're now in-servicing teachers and helping them get lessons that they can watch, view, and go into their classroom the very next day and implement. We're not going to use anything fancy. We're going to use graph paper, boards, etc. We're not going to have any animation or anything like that. But I promise, if you end up making it through this video, you should find something that'll work in your classroom. Even if you're a 6th grade teacher, 7th grade teacher in the middle school, should be able to at least help your students understand conceptual calculus. This is a long one, and we're going to thank you in advance for watching the whole thing. All right, let's get to it. For today's quiz, we have a sports photographer, and they are tasked with taking pictures for the local newspaper of the world's slowest race. And as the slow runners have already made almost a lap around the course, the photographer is going to pick up and snap some shots. They come past the start-finish line again when the photographer starts to snap pictures. And a lot of pictures. By the time they hit this 5-meter mark at 5 seconds, the photographer has the pictures that they want. They're going to submit the very first picture of them coming back around on the second lap at 0 seconds at 0 meters, and then at 5 meters at 5 seconds. Our question for today simply asks, what is the runner's overall speed? And what is their fastest speed? Here's what your quiz looks like today. I'll hold that up right now. As always, mark your answer as completely as possible and list your level of confidence. In other words, would you put $5 on your answer or $10 or no money whatsoever? Teachers that haven't asked their students to rate their confidence along with their explanation, you should start. It's really powerful. This little psychological trick lets the students know that you don't want some whimsical answer. You really want to know what they're thinking and why. The students also have something invested in the quiz, and they really want to know the answer now. These quizzes are supposed to elicit dialogue between your students, and teachers like to know what students typically say so they can prepare. So here's a typical set of responses that we get. Nearly all of the students will say, look, the answer is 1 meter per second. The runner is running 1 meter per second, and they will cite this as evidence. Looking at the newspaper, we are at the 0 mark at 0 seconds. At the 5-meter mark, it took 5 seconds. Case closed. Everyone is going to agree almost unanimously, aside from the one skeptic who says, look, we don't actually know what happened in there. I think the runner at some point might be going faster than 1 meter per second. The rest of the class looks horrified. How could you say such a thing? He says, well, maybe he slowed down and then at the end ran even faster to catch back up to get that average value. What do you think? Who do you agree with? The class or the skeptic? The students now have cognitive dissonance. While they all think it's 1 meter per second, after listening to the skeptic, they're wondering, could it be? Could they have slowed down and sped back up? So they decide to ask the teacher, can we please email that sports photographer and ask for one more picture? They do, and the picture comes back. And it turns out that the sports photographer said, well, I'll give you the picture at 2.5 seconds. And lo and behold, it's right in the middle, right here. At 2.5 seconds, they're at the 2.5 meter mark. Now the students are absolutely sure that they've gone 1 meter per second. 2.5 seconds, 2.5 meters. 5 meters, 5 seconds. Everyone knows the answer now for sure. Except the skeptic who says, wait, maybe they were there and then they realized they had dropped something and they ran back for it and went forward again. The class is now losing their mind and they say, maybe we should start to recreate this. And with the teacher's permission, they do it. The students formulate a plan. They say, first of all, let's get this to scale. We'll make 0, 1, 2, 3, 4, and 5 meters. And we'll literally put those in front of the room, measure them out, and we'll get a timer. We'll get a camera, and every time we have pieces of information, we'll let it go into the camera. And if we don't have information, we'll just black the camera out. And then we'll have the teacher walk this. We'll put all this together. Let's show you. You'll notice that the teacher is going to walk at the 2.5 meter mark. and it takes 2.5 seconds. You'll notice when he gets to the 5-second mark, he's at the 5-meter mark. Again, 2.5, and then 5 again. One of the mathematically astute students was working on the whiteboard as they were working up front on the blackboard. He ended up making a graph and calls the class over and says, look, I'm going to prove to you that this is 1 meter per second. Graphs don't lie. And if you take the slope of a distance versus time graph, it'll give you the velocity. He said, look, just using our 2 points, 0, 0, and 5 at 5, here and right here, we know that we can make a line with those 2 points. And we also had 2.5 meters in 2.5 seconds right there. And you can clearly see that the rise over run, which is going to be your velocity, is going to be 5 meters over 5 seconds. The skeptic responds by saying, wait a second, you have a line here. A line, from what I understand from geometry, is made up of an infinite number of points. We don't have an infinite number of points. We only have 3. We don't have a line. We have 3 dots that you thought was a line. He said, that's all we have. And then they ask, teacher, can we please ask the photographer for more data points? They email, photographer agrees, and as the data starts coming in, they realize that maybe the astute student was correct, because at the 1 meter mark, we had 1 second, and then we ended up having, at 2 seconds, 2 meters. Looking pretty good until the next piece of data comes in. Here you can see that as data comes in, we have more and more confidence that we were going at 1 meter per second up to 2.5 seconds. And everyone's very confident about that. That is, until we get information afterwards and we see literally you go to 2.5, go backwards, stop, and then run forward and end up at 5 meters at the 5-second mark. Clearly, we stopped, we went backwards, and then sprinted forward. Another student comes to the board and says, okay, here's what we thought. We thought that we had enough dots to draw a line for our distance versus time to give us our velocity. This is what we thought we had. Which would give us a velocity of 1 meter per second. But now we know we have more data. In fact, the runner actually stopped, went backwards, hung out, and then sprinted very quickly, and then ended up slowing back to a constant rate of that 1 meter per second as they hit the 5 mark at 5 seconds. Let's see if we can have each of the students now draw the distance and velocity graph for the real motion. The students rewatched the video over and over again, and they were able to get some definite points. They said, of course we had 1 meter, 1 second, 2 meters at 2 seconds, 2.5 meters at 2.5 seconds. And then they said, we actually went back to the 1 meter mark at about 3 seconds, right here. And we essentially stopped. We are at flat line. And then we had a very, very, very quick velocity back up. This is what it looks like. And the students are rather proud of themselves. Now we need to figure out how to do the velocity. To find velocity, let's use what our student told us earlier. They said if you just take the slope of a distance versus time graph, you'll get the velocity. Most students are really good with y equals mx plus b. And b would be our y-intercept, where it interacts with that y-axis, which is 0 here. So basically we have y equals mx, m being the slope. And if I have 5 meters in 5 seconds, the overall slope is 1. Let me draw that out real quick. Here we can see y equals mx plus b. Remember, b is just 0. Now I take the rise, how much I go up or down on the y-axis, versus the run, and that's going to be my slope. 5 meters is what I've risen, and 5 seconds is what I've run, and that equals 1, and that would be 1 meter per second. But for right now, we'll just use our slope as a 1, and we can see that that's like a normal slope. Well, we can get other kinds of positive slopes, like right here. Notice I can take this slope over here, it's still that positive. In fact, we can see the rise over run are both going to be positive. We know that up is positive and to the right is positive. So rise, run, and they're both positive and about the same size. So I could say positive over a positive equals a positive. But now when I take something that is lower than that, in other words, the slope is not as steep, well, now I have only a little bit of rise, but have the same amount of run. What happens then? Well, when I have a small positive over a normal positive, I end up with a small positive. So we would say it's still a positive slope, but it's less positive. And then a really, really steep slope like this, look, I've got a big rise, but a very tiny run. A very big number over a very, very small number is going to be a very large number. So this is a steep positive, that is a medium positive, and that is a small positive. See if you can do the same thing for the negatives. The negatives would be the same way, except in my rise on my standard slope would be I'm going to rise in a negative direction and still going to run in a positive direction. A negative over a positive equals a negative. But here you can see I'm barely rising in the negative direction, right? I'm dropping a little bit, but I still have a big run. A small negative over a normal positive is a small negative. And this is going to be a very, very large drop, negative, for a very little run. So large negative over a normal size or a smaller positive would be a large negative. So we have an array of slopes, very positive, medium positive, little positive. And then I have little negative, more negative, very steep negative. Now there's one more that we could say is straight across, flat. Here I don't have any rise whatsoever, so 0 over, no matter what the run is still 0. So that's our 0 slope. And of course, we never want to go straight up and down because that would be undefined. But using those values, we should be able to start figuring out how to do all of our graphs without numbers. But since we have numbers on this one, we can go back and see if we can figure out this velocity right now. But right away we can see that from that first part and the last part, we have a normal velocity. But when we went backwards, you'll notice that we had a negative slope. And then right here, we end up having a 0 slope. So that's going to lead us into our sprint, which is a very, very steep positive slope here. And remember, our distance is going to end up, the slope of the distance is going to give us our velocity. So see if you can make the velocity graph just by using the slopes, and we can put the numbers in after if we need to. We've now been able to make our velocity graph. Let's think about the runner coming past the start-finish line. They're going at a constant speed of that 1 meter per second. Now, of course, they're going to end up going backwards, stopping for a moment, and then sprinting very fast, and then they're going to end up walking like they were going the normal speed again. So at first, we end up getting a slope of 1, and at the very end, 1. So our velocity here is 1, and at the very end, it's also 1 again. But right here, we end up getting a negative slope, and so we're going to end up having a negative velocity. So whenever we say negative slope, we're talking about negative velocity now. And you'll see that we have a negative part of our graph that we had to make. So during this little period, when they're going to experience a negative slope. They're going backwards. Right here, they stop. So right here, their velocity is 0. And then we get a very, very fast velocity indeed, that sprint right here, which corresponds to that large slope. And then we're back to our normal 1 meter per second. Look, we don't exactly know every single point in between here, and that's the problem. We asked the photographer for more and more photos, but even a camera would only flash 30 times a second at most, or something like that. So we don't have all of the information. But that's the essence of the idea of calculus. Could we end up getting information between those dots? And if I took 60 dots in between those two dots, and then 60 dots in between any of those two dots, and do that over and over till we end up with an infinitesimally small value between them, we would actually know it's always happening. That's the essence of taking a derivative in calculus. And that is what our students can learn. We can say, whenever we're taking the slope of a line, we are of a distance versus time line, we are getting the velocity, also known as a derivative. Now, one of the great things about just using slopes are more intuitive for students, and we now have some modern technology that can help us get a really good intuition for what this motion looks like and feels like. If your school was fortunate enough to have the Vernier system or anything like it, I can use one of these old LabQuest minis, and I've got my motion sensor right here. I just connect it right to the edge of the desk, and it'll pick up my motion in real time. I'm going to try and match that black graph there. So it says I need to be close at first, and then I'm going to go further away. So let's give this a whirl. I'll start right here, and I'll start moving back. Look, I'm trying to make my line on top of that other black line. And then I'll go back as such. It's a really great activity to help your students gain an intuition about how motion can be graphed. And if you need a real challenge, you can try to walk the velocity graph. Now, these are never going to be as smooth, but we can try this out. Let me see if I got this. Notice I'm going to try and shuffle backwards, and then I'm going to go back towards the sensor, and then I'm going to go faster on the backward motion. Again, not perfect, but you can see in general, what do we mean by constant motion? What do we mean by accelerations or jerks? Now, that term jerk is not someone in the stands yelling at the runners. Think of that being a change of acceleration. Maybe you're accelerating in your car and suddenly you get a bump or something like that. That's a changing acceleration. That gets more complicated. One of the things that I wanted to point out is that modern technology is wonderful, but it's no panacea. I think that you saw that you had a lot of noise that was introduced whenever you were trying to walk that velocity graph. And that's because even that sensor, which is pinging out ultrasound and it's bouncing off you and going back to the receiver, it doesn't have every data point, right? You can literally hear it clicking. And in between those clicks, just like our dots here, we don't know exactly what's happening. So maybe to get a more idealized case of this, what we can do is just walk some very simple graphs. Just to answer our questions from the quiz, we can say that overall we did have a velocity average of 1 meter per second, but our top speed was way faster than that, and that's because of the trickery that the runner was playing on us. After the race, everyone wants to come down on the field and practice their walking graphs. Now, I have a distance versus graph ready to go here. We'll do a velocity and we'll introduce the acceleration. Let's still use the same track, 0 to 5 meters. And let's say that we come walking past at a nice constant velocity. Notice I started at 0 and I'm getting further and further from that in a positive direction. So this would be a positive distance, this would be a more positive distance, and the most positive over here. So at first, I came through and I was getting more and more positive with my distance. But then, let's say I decide that I want to come right back. So here I'd be going from the greatest positive to a little less positive, and back to 0. So instead of using real numbers, let's just use big or small positives, negatives, and so on. See if you can make that graph right now. Here's what our graph looks like. you'll notice that I'm going to the greatest positive distance and coming back. Now, to make the velocity graph, let's just think about the actual motion. Notice I was going at a nice constant velocity here, and then when I came back, I was going at a nice constant velocity. This one just happens to be negative. So in other words, if I had a speedometer on me, it would always be the same. And then if I went backwards, the speedometer would still be reading a nice constant value, just going in a negative direction. See if you can make that velocity graph. All right, here's what our velocity versus time looks like. You'll see that it's going to be a positive velocity going to a negative velocity. And that's what it should be. Look, I'm going a nice constant positive velocity, and then I suddenly am going a nice constant negative velocity. Our problem occurs right in this spot right here. Notice over here, my speedometer had to go to 0 when I'm at my furthest positive distance, and then I need to start coming backwards. And it's going to be very steep here, but I can never have that going straight up and down. That would be instantaneous in time, and we don't want that. And we also know that if we ever take the slope of that, we're never going to be able to because that's undefined. The key here is we take the slope of our distance versus time. Like for the first part, we see a nice constant positive slope gives us a nice constant positive velocity. On the way back, we can see we can have a nice constant negative slope, which gives us a nice constant negative velocity. It's this part right here that we want to concentrate on. Let me blow that up and let's show you how to deal with that. What I've done here is I've simply taken that little area that we were interested in, and I'm going to kind of spread it out and maybe magnify it. So that straight up and down line is really going to end up looking kind of like this nice curve. Now, we found out that if we take the slope of a distance versus time, we get the velocity. What we're also going to find out is if I take the velocity versus time graph and take the slope of that, I'm going to end up with acceleration. This will kind of lead us right into that. Now, we have to understand that we are going to need tangent lines. And tangent lines are, think of if you just wanted to approximate along a curve what the single slope would be at one point. So right here it would be 0, and then it starts to get a little bit more negative, a little bit more negative, a little bit more negative. In fact, right at our midpoint of that curve, notice I'm the steepest I'm ever going to be. And after that, I get less steep, but it's still going to be negative. Still negative, but less steep, less steep, less steep, less steep, back to 0. Now, that might seem like a lot, but I think we can do this pretty easily if we look at the easiest points. The first point right there, I think we can all see that is a 0 slope. At the end, we're going to be a 0 slope, but we're only there for one point in time. So I can end up putting a 0 dot there and a 0 dot there. We also know that in the very middle, halfway between, I'm at the steepest negative I'm ever going to be. So I would go down to my greatest negative, put a dot here, and then I can start working on the intermediates. Notice right here, I'm going to be a little bit, so I started at 0, a little bit negative, a little bit more negative, a little bit more, most negative. So in other words, I'm getting more and more negative over time. And then you could see that I start becoming less and less negative over time, back to 0. So I end up trying to blow that up. It's going to end up being a little spike. So what do we have right there? We have a little spike right here. A little negative spike, but now we can do our first acceleration graph. Because what is our velocity for the first part of this? Look, I'm not changing my velocity. I'm not accelerating. And on my way back, I'm not accelerating either. It was only when I got right here, boom, now I put on the brakes and I put in reverse. And now for that very short period of time, I had a negative acceleration right here. And that's why we are going to end up putting a little spike on here. Other than that, though, we essentially have no acceleration. The entire time we were going across, I'm not accelerating, and then on the way back, I'm not accelerating. It was just right here. And you could think of someone pushing you to accelerate you, and that's that little spike. So without technology, you can do this with your students. And by the way, they get a kick out of this. And the reason why students get a kick out of this is because they can solve problems that they had a difficult time with before. Let me just give you one example. This is a quick quiz that we run, and we ask, we're going to have a golf ball, you throw it up in the air, it's going to come back in your hand. What is the acceleration right at the very top, right when it hits the top point? Let me hold that quiz up for you right now. As always, we want our students to mark their answers as completely as possible and list their level of confidence. The typical answer that we get is, at the very top, the acceleration is 0. And almost all of the students put that. However, if you have one student that recognizes that they could possibly graph this, they're going to say something different. And they're going to say, it's not 0. It's going to be negative. And the students are perplexed by this, and they're still going to end up saying it's 0. Before we provide an explanation, you can ask your students, what would the distance versus time graph look like? Think of you're throwing a ball up and down, but we're also going through time. I'm here at 0 seconds, then I'm here at 1 second, then I'm here at 2 seconds, 3 seconds, and so on. Time goes on. So what would a ball look like if we were to throw this up in the air, but go through time? Let me try it once more, going through time. I hope everyone can see the shape that that makes. Give them that hint before we give the full explanation. All right, I've drawn a picture of what the shape looks like when the ball is traveling, and it looks like a parabola. A little harder to draw than I thought, but now what we can do is we can use the idea that if we take the slope of a distance versus time graph, we'll get the velocity. And then if we take the slope of a velocity versus time graph, we'll get the acceleration. So when we look at this arc, we can see a couple dead giveaway points. Remember, we're going to use these little tangent lines, the lessons that we learned earlier. And I hope everyone can see, just like our students normally will, at the very top, right up top there, we end up having a flat spot. And then at the beginning, well, let's do that first. So we end up having a tangent line that's going to end up being flat. Now, what does a 0 slope give us for our velocity? Well, you just replace the word slope with velocity. If I have a 0 slope up there, I have 0 velocity there. So right down there, I would put 0. Now, a lot of our students are going to feel vindicated. They're going to say, look, we put 0. But remember, that's velocity. We're asking for acceleration. So we need to make the rest of the graph. Well, I think most of us can see at the beginning of that graph, we have a very, 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 very steep tangent line. And so it looks something like this. And that means we're never going to be that steep again. Look at that. So right at the beginning of our velocity graph, we'll end up with a point right there. At the end, we're going to end up having a tangent line that is very negative, never going to be that steep again. So at the end, we're going to end up being at our negative. Right away, I'm starting to think that it might be linear. I think we can kind of line those up. Let's go for one more point in between. Well, if I went somewhere about right here, and then I used my slopometer, I could see, well, that tangent line is going to be maybe like a medium, small, positive. So come straight down, medium, small, something like that. And then if I put a point right here, and remember, the more points you do, the more accurate you're going to get your transfer. A negative, medium, something like this. Maybe I'll do one, so that slope was here, that slope was here, that slope was here. Maybe I'll do one right here. And that's just a slight bit negative. If I were to bring that straight down, yeah, I'm feeling pretty confident. This is going to end up, for the most part, being a nice straight line. And that's what our velocity versus time graph gives us. Now, why is that significant? Because remember, once we have the slope of a velocity versus time graph, we can get the acceleration. All we have to do is take our slopeometer and we say, oh, it's always negative, a medium negative, never changing. And that means our acceleration is medium, never changing. And so, and it's negative. Medium, negative, never changing. Our acceleration is medium, negative, never changing. And therefore, notice we always have a negative acceleration. Now, at that point, they might already know that gravity pulls down at negative 9.8, and gravity is always pulling down. You can see that if you use your graphs, you're going to be in much better shape. All right, we've learned a little bit about calculus already. All we need to do to go down from distance to velocity to acceleration is take the slope, also known as taking the derivative. The obvious question is, can we go back up? And the obvious answer is going to be, of course. And that's called integration. And all we have to do, instead of taking the slope like we are coming down, we go back up by taking the area under the curve. Now, to simplify everything as much as possible, I've just made values that are super easy to do in our head. Let's say that we have a constant acceleration of 10 meters per second squared. That means I'm always picking up speed. Now, at 10 meters per second, after 1 second, I can take the area under the curve by simply making a little rectangle. So I'll take this down here, and I can say, take that area. Area is simply length times width. 10 times 1 is 10. That takes us up to our velocity. Our velocity at 1, we'll say, is 10. Now we can do the next block, and that would be 2 times 10, like this. And now I could do it two ways. I can either say, what is the total area here? Or I could say, well, I already had 10, and now I'm going to add another 10. Regardless, 2 times 10, the total area under the curve at 2 seconds is 20. So I'll put a little mark here at 20. And then I think you can see what's going to happen for the rest of these. As I add another one of these blocks, and this is the simplest case we can think of, I'll now add another 10. I already had 20, so it's going to be 30 total. You could also say, look, this big rectangle now is 10 times 3, and that's 30. Put it right there. And then 4 times 10 is 40, so we're at 40 at the 4-second mark. And then if we did the entire thing, it would be 5 times 10. Or you could say I had 40, add another 10. So I'm now at 50. And we end up with a straight line. Or something close to that. Do you think you can do the acceleration by taking the area under the curve as we just did? Before I do it for you, see what you can do. Hopefully you tried this and recognized that you're not going to be able to make rectangles as easily on this one, but we can end up forcing them to be triangles. Let me just show you. It'll be easier. Look, I could have ended up saying, I want to make a rectangle right here, 10 and 1. And I don't want to take the entire area of that rectangle because it's really this triangle that I'm looking for. So let's just take the rectangle, cut it in half, and that'll be the area. So 10 times 1 is 10. I only want half of that. So at 1 second, we'll be at 5. Now, I've already made my y-axis here. 5 is going to be really far down here like that. Let's do the same thing with 2 and 20. Might be easier just to do the entire thing all at once in this case. If I ended up trying to find this total area now, I could take 2 times 20, which is 40. But remember, I only want the bottom half, so that's going to end up being 20. So 2 would be at 20 right here. And then I'll do the same process again. I'm going to use the whole rectangle just to make my life easier. This is 30 at 3. And that's going to be 90. Take half of that, that's 45. So I'm at 45, probably something about there. And then 4 at 40 is 160. And we're going to take half of that, that would be 80. So we can see that this is not looking linear. Let's do our last one. If we did the entire thing, and then I just want to end up taking the area of the bottom part of that triangle. 5 times 50 is 250. So at 5, half of that would be 125. I think that's right about there. And I think we can see that that is going to be some kind of curve. It's no longer linear. And as I made these little rectangles smaller and smaller and fit more of them in there, I would get more and more data points, and I'd have more confidence in what that curve is. Now, I'm just going to show that it's probably going to be, now this is a pretty hard curve. Looks like a curve like that. Pretty cool. This video is not meant to be exhaustive in its exploration of calculus, but we do understand that students are going to eventually learn there are canonical ways of solving calculus problems, and that of course includes formulas. And one of those formulas is the power rule, and we're dealing with polynomials and things of that nature. They work pretty well, and they are straightforward, and most students learn this quickly. They also learn that you can end up going back up. So when we're coming down and taking slopes of lines, we're taking the derivative. So we go from distance to velocity to acceleration. And then we can work back up by taking the area under a curve. And those are called taking the integral, or integrating, going back up. And we have a formula for that. But this has been done elsewhere, and you can go elsewhere to find examples of this. But we feel that students, maybe as young as 6th grade, should and could understand the basics of calculus. And so that's what we're going to aim for, an alternate technique of doing some integration. Now, we're not going to give a formal quiz at this point. We don't want teachers to get the impression that they have to have some paper in order to teach that lesson. If you have graph paper, just write it down on your graph paper. If you don't have that, write it down on the board. Let's just jump right to that quiz. It simply asks, if I have a velocity on my y-axis, this is velocity versus time graph, 25 seconds, and we have someone that's running that 5 for 25 seconds. We simply want to know how far do they go if they are going at that constant 5 after that 25 seconds, as opposed to, let's look at the second graph, which is certainly going to look different, where we're starting at 0, going faster and faster and faster, and then slowing back down to 0. How far would this person go compared to the person that was running that graph? And then, of course, we can look at the bell-shaped curve type of graph. How far would they go? Would they go further? Not as far? Same distance as the others. And then, of course, we've got the one that looks like a parabola, and we had that shape when we did the ball throw. Now, I want to point out that the middle two graphs peak at 10, where the top is a constant 5. And this bottom graph does not peak at 10, a little bit less than that. Before we go over the answer, we'd like you to see what your answer is. Typical student responses are usually that this peaks at 10 and this one peaks at 10 and the others do not. Therefore, it's going to be one of these two that goes the furthest. Now, you might want to just push them on this and remind them these are velocity versus time graphs. And if you've done any of the lessons with them before, remember, it's the area that ends up telling us about the distance, the area under the curve. So if we can integrate those, we'll get the answer. See if that helps them at all. Hopefully some of your students will say, yeah, we can integrate these. Now, you could have these ready for them, or you could give them graph paper. And that is a nice way to consider finding the area. And you'll notice that I have each of these. Now, I also put negative numbers on each one of these sheets, and I realized it would be a little bit too cramped on the board here, so I left the negatives off. That actually makes it easier. So there's our first graph. Here's our second graph, our third graph, and our fourth graph. You can also photocopy this if you're rushed for time, or you could have the students make it themselves. I'll put all four side by side and give them a little bit of time to think. Most of your students will actually physically count the number of blocks. Pretty soon, someone will say, you know what, there's an easier way than counting these blocks, especially on this first graph. All we have to do is take 5 times 25. We know there's 125 there. But these other two turn out to be rather difficult. They have to come up with some kind of rule system. Like, in other words, what do we do if I only get 3/4 of a block or half of a block? Something like that. But a lot of them will end up thinking about symmetry of maybe the triangular one. Let's see what they can do. Many of the students are just going to use a grunt method. And here's the values. I literally had someone count them, and these are the values that they got. Of course, this was 125 right here. So this one here, they got 121. But right away, as soon as we say that, someone else is going to inevitably raise their hand and say, no, no, no. This is 125, and so is this. Because if you end up taking this triangle right here, or better yet, half of this triangle, take that triangle, fit it right up in here, you make half of that rectangle, which is going to be 25 times 10. Take half of that, and it would also be 125. That's when you hear, oh, you're right. It must be. That also tells us that when we're trying to count our triangles, when we go halvesies or 3/4 or 1/4, you definitely are going to have a little bit of error there. So let's make this 125 here. Oh, that looks ugly. And then we're going to end up trying to count these two. Now, some of the students will end up counting this one and say this is about 120. And then finally, this one down here is 147. So that looks like our order. But this one was really hard to count, and everyone knows it. So they don't have as much confidence because there's more and more of these different size triangles there. And that's what we really want to show them, is understand the limits of your technique. The students are not terribly sure of that last technique, so we're going to show them one more. I've got this big light that I brought over, and here's our standard triangle, and then I also have our bell-shaped curve. Now, what I'm going to do is I'm going to stack them on top of one another so that we can see in here. You'll notice that we can see the one behind the other. Notice this is a little bit on the inside of the triangle, and that's a little on the outside of the triangle, which means they're going to balance out. So in other words, I have as much outside of that triangle as I do on the inside on both sides, so both of these are also going to be the same. Let me show you one more alternate technique. Sometimes your graphs are going to be so complicated, it's going to be very hard to get any kind of symmetry, and trying to count individual blocks is going to be a problem. Now, the point of calculus is the smaller that we can make things, like instead of having a big giant block, and if I miss part of that, I'm really off. If you could get those blocks smaller and smaller and smaller, you're going to have less and less error. Now, I'm going to simply cut each one of these out, and then I'm going to weigh the paper for each. So, give me a moment while I cut these out. All right, we've cut all these out, and we are ready to go. All right, so let me put each of these on the scale. I'm hoping the camera will see it. This is very, oh no, I can't see it. All right, so I'm just going to try and balance them at first. This is 1.18 for our largest one. Our square it's jumping around, I'd say 0.96, 0.97. Let's do our triangle. 0.96, 0.97. What's the one I didn't do yet? This one. 0.96, 0.97. So they really are the same. And this is a really good technique where you can cut these out. Now I could probably also fold them and see if they can stand on their own. And that works. 120. And you can see that I didn't do a great job of cutting. There's still a little extra blue on there. Let's see if this works even better. And this is the whole point, 0.97. You end up finding better and better techniques. And this is going to lead us into one of our last ideas that we would like all students, 0.97, to end up trying to do a long term with math. Oh, that one's not balancing. Oh, really difficult on this one. 0.98. All very, very close indeed, aside from this one right here. So that is a new technique. But using this kind of ingenuity to try to solve problems is how science ends up making some serious gains. This is a real-world application of graphical analysis. Before we had modern computers that could simply add up all these infinitesimally small little values on a computer just by grunt programming, we had a hard time trying to figure out what was the area under a curve, especially really complicated curves. But we had accurate scales for some time. We literally would end up weighing them to find their relative size versus something else. So this is a viable technique and has been used for some time in science. We wanted to take just a moment here to justify how we could use a scale to end up giving us area. And remember, we found the area of the three graphs of our triangular graph and this rectangular graph were equal. And heck, we could use symmetry on these. But the bell-shaped curve and the parabola were much more difficult, so we ended up using that scale. Now, scientists, engineers, mathematicians need to justify their work. We're going to base everything on this piece of paper. We're going to say it's uniform throughout. And so let's give a few variables to this. It's got a certain density. It's also got a depth to it. So we can end up saying that we're trying to make the claim that even though we don't know the absolute value of any of these, we can simply take the ratio of them to get some kind of correspondence. So our claim is the weight 1 versus the weight 2 of our areas, area 1 and area 2, will be equal. Notice our notation, we'll use A for area. Everyone knows length times width. And then we can say depth instead of thickness. And density, we use the Greek letter rho, and that is mass per volume. Weight is mass times gravity. Gravity acts on all masses. And volume is our area times our depth. We could start right away just by saying weight equals mg, and if we end up wanting to get mass, we can end up taking our rho v right from our density formula. Students that are used to doing dimensional analysis should be able to follow along with this without a problem. We'll then take that rho v, put it right here, bring down the g, so we end up with our weight being rho vg. We also know that v can be our area times our depth, and we'll put those in for our v. So I've got rho a dg. Now when I put one on top of the other, weight 1 over weight 2, notice we're going to have most things that are going to be constant, simply crossing out. The paper is the same for all of these. So rho crosses with rho, a1 over a2, depth, they're both going to be the same piece of paper, they cross out, and so does gravity. We can therefore say that weight 1 over weight 2 is equal to area 1 over area 2. Now, some might be sticklers and say, hey, that's really a weight scale that is giving you mass and you gave us mass. Fine, if you'd like to go the next step, this is technically a weight scale, but it's been calibrated to work on Earth. In other words, whatever we put on there, G is going to act the same. So we could go one step further if you'd like and simply say each one of those weights is going to be a mass times a gravity. So M1 over M2 is equal to area 1 over area 2. Either way, this is how you might justify your claims. All right, let's wrap this up. Just to be clear, these three graphs would give you the same amount of distance. Why? Well, they have the same area under the curve. And even though this parabolic one did not peak as high as the two above it, it actually had more area, and therefore you would travel the furthest. We thank you if you've made it through this part of the video, and we're hoping that you're going to be able to take something into your classroom, hopefully tomorrow or the next day. We normally say, that's your quiz for today, but we did multiple quizzes, so we'll say, those are your quizzes for today. Thank you for watching another Idealized Science Institute video. We are a nonprofit organization. If you like what you've seen, be sure to like and subscribe. And if you want, leave a comment below. It's helpful to us. If you can financially support us, go to our website and hit the donate button. If you can't, simply by sharing these videos with other teachers and students in your life will be helpful. While at our website, you'll find that we have our Idealized Science Institute book that'll help you engage your students in dialogic discourse. There you'll also find we have a podcast where we break down educational research. We also have long-form lessons. If you're a teacher, you can watch these and go in the very next day and enact these. Along with this, we also have many other resources, including more quick quizzes. So thank you for watching, and we hope to see you in the next one.